Energy is the fundamental currency of the universe. It cannot be created or destroyed, you only transform. This is the first law of thermodynamics, and it governs everything from stars to smartphones. When you move, think, or even breathe, chemical energy stored in molecules converts into mechanical and thermal energy. Energy is constantly changing form, but the total amount remains constant. In physics, energy appears in many forms: kinetic energy of motion, potential energy of position, thermal energy of heat, electromagnetic energy of light, and nuclear energy inside atoms. In his 1905 Annus Mirabilis papers, Einstein showed that mass is his equation, E equals mc squared. This means matter can be converted into enormous amounts of energy. Stars shine because nuclear fusion converts mass into energy. In our sun, hydrogen atoms fuse into helium, releasing radiation that powers life on Earth. For centuries, scientists assumed the universe was static. But in 1929, Edwin Hubble observed that distant galaxies are moving away from us. This discovery showed that the universe is expanding. The farther a galaxy is, the faster it recedes, a relationship now known as Hubble's law. If the universe is expanding, gravity should slow it down. Matter attracts matter, so the cosmic expansion should gradually decelerate over time. But in the late 1990s, two independent teams studying distant supernova discovered something shocking. The expansion of the universe is accelerating. This meant there must be a mysterious force pushing space apart, overcoming gravity. Scientists called this unknown component dark energy. This meant there must be a mysterious force pushing space apart, overcoming gravity. Scientists called this unknown component dark energy. Dark energy is not ordinary energy like heat or light. It does not emit radiation and cannot be directly detected. Its existence is inferred from cosmic acceleration. Dark energy is not ordinary energy like heat or light. It does not emit radiation and cannot be directly detected. Its existence is inferred from cosmic acceleration. Observations of the cosmic microwave background from missions like Planck helped measure the universe's composition. The results were astonishing. Only about 5% of the universe is ordinary matter, around 27% is dark matter, and nearly 68% is dark energy.
Dark energy appears to be uniformly distributed throughout space. Unlike matter, it does not clump together into galaxies or clusters.
One leading explanation is the cosmological constant, first introduced by Albert Einstein in his equations of general relativity.
The cosmological constant represents the energy density of empty space, also known as vacuum energy. In quantum field theory, even empty space is not truly empty. It contains fluctuating energy fields, constantly producing and annihilating virtual particles. These quantum fluctuations suggest that space itself possesses intrinsic energy. This vacuum energy could be responsible for cosmic acceleration. However, theoretical predictions of vacuum energy are vastly larger than what we observe, creating one of the biggest puzzles in modern physics.
Another hypothesis proposes a dynamic field called quintessence, which changes over time and drives expansion differently from a constant force. Another hypothesis proposes a dynamic field called quintessence, which changes over time and drives expansion differently from a constant force.
To understand dark energy, scientists study large-scale cosmic structures, galaxy clusters, supernova brightness, and gravitational lensing. Precision measurements of expansion rate are ongoing, and small discrepancies, known as the Hubble tension, may hint at new physics. If dark energy remains constant, the universe will continue expanding forever. Galaxies will drift apart beyond visibility. In this scenario, stars will eventually burn out, leading to a cold, dark cosmos, a state sometimes called the heat death of the universe. Energy will still exist, but it will be evenly distributed. Without gradients, no useful work can occur. However, if dark energy grows stronger over time, it could lead to a big rip, tearing galaxies, stars, and even atoms apart. Dark energy drives the universe's accelerating expansion. Conversely, if dark energy weakens or reverses, gravity might eventually dominate. potentially leading to a cosmic collapse. Understanding dark energy requires combining quantum mechanics and general relativity, two pillars of physics not yet fully unified. Future observatories and space telescopes aim to map billions of galaxies to measure cosmic expansion with greater precision. Energy shapes the stars, fuels life, and governs motion. Dark energy shapes the destiny of the universe itself. What began as a simple question about expansion has revealing that most of reality is still unknown.